Good afternoon, everyone. We'll start our meeting today with Lucia's talk on dark matter boosted by terrestrial collisions. So let me.
Okay, thank you very much. Can I start? Okay, thank you very much. Today I will talk about a paper that was submitted on arXiv this week in the past for October 14. Basically, uh, they are exploring inelastic dark matter in direct detection experiments. So what they are saying is that for decades, uh, the scientists have been looking for dark matter in direct detection experiments, but we didn't have a good result until now. And this could be because two reasons, reasons. It could be because the dark matter could be very heavy and it readily pass through the detector, or it could be because the opposite reason. It could be because the dark matter is lighter enough to be invisible in some way to the detectors, so it doesn't activate the sensors, something like that. Another possible scenario they are exploring here is that basically the dark matter could be the interactions between dark matter and standard model particles could be mainly inelastic, and this could be have some energy threshold that in some way suppress offer this kind of scattering with the laboratory target. That of course, as usual, it could be xenon or argon. So dark matter particles, in this case, they are trying to see a model where there is the dark matter that we know is denoted by K1 here with a mass N1, and it could in some way interact with a nuclei, for example, and be inelastic. But how this could be this could happen? It could be because via loop, and but it is assumed that this could be the limit of the mass in via loop is very heavy and it's suppressed. So in this case, they are neglecting this case, but it could be they are also exploring at tree level. Uh, but here the dark matter particle that will be this key one cannot scatter with elastically with the standard model particles, and it in some way excites this first state and converted in a second state. So as you can see, we have a first state that it will be K1 that interacts with the nuclei, and from this interaction, it could be excited and it will gain some kinetic energy and will be a second state that is called K2. In this case, in order to be this possible, they require that the total kinetic energy of this process has to be proportional to the mass splitting. The mass splitting is denoted by this sigma, that basically is the difference between the mass 2 with the mass 1. So the second state with the first state. They are basically they are saying this in the introduction. They are also saying that in previous works, it has been explored in elastic conversion of kit 1 to kit 2, but it is assumed that the kit 2 could decay electromagnetically, or it could in some way interact with a electron via dark photon. So this has been explored in the literature, and they also here, what they have done is to use the two data sets from two experiments of direct detection, that is Shannon 1T and Shannon 100, and to construct the limits for this model they are presenting today. Okay, so to understand the kinematics of inelastic dark matter, we have to take into account that both processes are different. The upscattering is when the dark matter particle will acquire a mass and a kinetic energy. And downscattering is when the dark matter particle will lose energy and will lose mass. So this is a key point because it could be confusing in the future. So what is happening? We have the dark matter particle, Q1, that is coming with a certain velocity, and it will collide with a nuclei of the Earth, of our planet, and it will be excited. It means that it will be upscattered. It will gain some kinetic energy, and after that it will travel to the detector. Once it reaches the detector, is passing through the detector, it will collide with the nuclei of the detector. In this case will be xenon, and it will downscatter. It means that it will be again to the key one. So what is the transition? Key one is excited, it is going to the key 2, and after that, when it reaches the detector, it will go back to the state of. Is clear until now this? Okay, I assume that is good. Do you understand this? What is the dynamic? Okay, perfect. So basically, in order to do the calculations here, they are assuming that the mass of the dark matter particles is 1 TeV. Okay, sorry, what? Yeah. Here. Okay. Here, just remembering that we are in initial stage, we are dealing with a key one particle that will be excited. It will be transferred in key two, and this mass M2 will be denoted by this equation here, where we have the initial mass of the initial dark matter particle, N1, plus the mass splitting, that is the difference between the M2 state and the N1, okay? To do the calculation, they are assuming that the dark matter mass is 1 TeV. And in the first case that it will be upscattering, they are assuming these kinematics where they are, of course, taking into account the energy conservation, where we have here in the left side, we have the initial state, and here in the final state, we are taking the mass of the second state, that is M2, with the final velocity of the dark matter, and here they are increasing a term where we have the mass of the nuclei they are dealing with and the final velocity of these nuclei after the scattering. Here they are also increasing with the mass splitting I explained before. So in order that this happens, they need to have a very clear energy threshold, and this energy threshold it could be in some way translated to the initial velocity of the dark matter. So this is denoted by this equation here that depends of the mass splitting I mentioned before over the reduced mass between the nuclei and the inelastic dark matter. And this is the threshold energy in this case for the upscattering. But for the downscattering, there is no like a minimum energy to lose, but they have to take into account uh, the how much was the momentum transfer that is denoted by this one, this equation here. And they also are assuming an angle of that give us 180 that give us 1 in the cosine of theta. Okay, in order to calculate the minimum velocity that requires in order to produce a energy recall that could be detectable for my data detection experiments, they calculate this based on this equation here, where here is the mass of the nuclei, this is the energy recoil, this is the mass reduced, this is the mass splitting, and so on. What else? Okay, the mass splitting that they are taking into account requires it is they are limited in the order of keV, and requires a velocity need of the maximum velocity of the dark matter, searching for higher energy recoils because it could in some way increase the event rate. In this case, this is what they are doing here, and here doesn't say anything more, anything important, but here they are explaining how is the mechanism and the considerations they are taking into account. So in order to perform this calculation, they use the local dark matter density to be 0.4 GeV over centimeters square now, 3 and a 3. And here they are saying, you can say, but yeah, the Earth, our planet, is made of many elements. How they can just perform this calculation? So in this case, they have used just one. That is the one that is composing the mantle and the crust. And in this case, they perform the calculation by using lead. And yeah, this is the consideration they have done here. Mm, Here, in order to take into account the dark matter velocity, uh, they have two considerations. They are a standard model halo, and they also have enhancement that is coming from the Large Magellan Cloud. So, what they are saying that is the dark matter is coming with a dispersion energy of 200 with a dispersion velocity of 220 kilometers per second, and the velocity escape of the from the galaxy it will be in the first moment 540 kilometers per second. After that, this is the dark matter is excited in some way, it will reach for each of these values 300 kilometers per second, and it will have the maximum velocity of escape of um, 800 kilometers per second. Here they have two observations, the observation from Gaia and the observation for the Large Magellanic Cloud. I don't know how to pronounce this. But yeah, so in this result that I will show here, they are taking into account the standard halo model, the one that is here, yeah, with these lines here. With this continuous line, they are taking into account the enhancement of this LMC. Here, in this case, the red ones are for upscattering, as you can let me just explain again. Here they are denoting the fraction of dark matter that could supply the minimum velocity that they have calculated versus the mass splitting. So they have done the calculations for upscattering and for downscattering. In the first ones, in the continuous lines here, they are taking into account the contribution and enhancement of the large magnetic clouds, and here in the ones that are not continuous, they are using the just the standard halo model. Yeah. Uh, so they are using two data sets. Uh, One is from Shannon 1T, and here they are using looking for a fraction of dark matter particles that could produce this Shannon recoil, and they are checking in this energy threshold that could be between 4.9 keV and 40.9 keV in order to illustrate the things. In the second, uh, yeah. Now, in order to calculate the event rate, uh, they are calculating the probability that this kind of process could happen with the key one passing through the air and collides with the lead. And after that, down scatter with the nuclei that is composing the experiment. They are calculating this probability of this process happened, that where here, this is the number density of the lead. Here we have the cross section between uh, the nuclei and the dark matter, and here this is the distance of this could happen. And here, this is denoted by the cross section is proportional to this here. And here we have the distribution here. And here we have the distribution of the velocity of the minimum velocity that could be reached for these mechanisms in order to produce this energy recoil. What else? I think that, yeah. What else? Of course, in order to integrate this equation here with the distance, they are using 1 kilometer and this 2,700 of kilometers, in case that is the diameter of the Earth. And in order to do this calculation, they neglected other relatively light elements that could be found during this travel. And they also take into account different scattering angles for this process in order to cover the area, the bigger area that they could supply with this kind of experiment. What else? In this case, they also neglected the that maybe when it collides with a nuclei, it could change of direction. They are not assuming this because, as you can see, the dark matter is 1 TeV, and this is very is heavier than the normal mass of a nuclei. So what they are just neglecting that this could have a very different trajectory after the collision. Here, in this case, they have calculated the rate in the case of down scattering. And here, they are taking into account this equation here, that basically is the integration between the number of density of the xenon, that this is for the detector. As I said, this is for down scattering. And the difference, the main difference is the energy threshold here, because as I said before, the down scattering doesn't require energy threshold minimum, but it has to supply the equation that we saw before about the transfer momentum denoted by K. What else? Yeah, they are taking into account some corrections, and these corrections here are based basically that maybe during the travel between the up scattering and the down scattering, it could collide with another things. So they did the calculation, assuming, for example, that the air is made from silicon, and they calculate the probability that the dark matter particle will not down scatter after this collision here. So all these corrections has been taken into account. Um, and here they are showing the results. So for the first data set, they are using 1 ton-year exposure for xenon 1T, and they are looking for nuclear recoils with energies between this range of energy, and they didn't see any significant excess over the background. And in the second one, the Xenon 100 could extend energies until 240 keV, and they didn't see any significant increase in the excess of in the background, but they have obtained some very good limits here. So I will show here in this figure. In this case, this is for Xenon 1T. As you can see here, this is this work. This is the a bigger cross section that you could reach with this kind of processes, and that has been constrained in the past with another experiments. But in the case of this model, they could reach this until a mass splitting of almost 350 keV. That is good. And it is just only shadowed by this Lux Panda projection that is not ready now. And they also did this same graphic for the Shino 100. And here they showed um, both results. The first one, that is this one, the one that I presented before, that it could reach 300 with 50 keV. And now with this experiment, with this data set, they are increasing this until almost 800 keV. So it's a very good result. And yeah, and the conclusion of this paper basically is that they have studied the excitation of a dark matter particle that is coming to the Earth with a certain velocity, and it could be upscatter and after that downscatter, and could be detectable in the traditional direct detection experiments that we have until now. So it's interesting, and it could be a good option to explore in this parameter space. So that's all. Okay. Yeah, downscatter. Downscatter. Yeah. Yeah. Well, now you have to take into account this. In the dark matter particle is not upscatter into the detector. It is upscatter before it reaches the detector. After that, it arrives with a certain velocity of the upscattering, and when it collides with the nuclei in the detector, it will be downscatter. And the reason why they have chosen this kind of mechanism is because the upscattering has been explored in the detector in previous works, but it didn't give a good result. Yeah, in this case, they are exploring this because they mentioned that the upscattering has been explored and actually is the traditional form that they explored the inelastic dark matter in indirect detection experiments, that the dark matter upscatters in the detector, but unfortunately they didn't have a good results. So now they are doing the opposite to prove that maybe dark matter could lose kinetic energy by colliding with the nuclei in the experiment and could be detectable with the traditional that we already have built. Yeah. Mhm. Yeah.